Friends, welcome to the 26th lecture and module 1. We are now going to apply the concepts what we studied for 3D analysis onto a 3-dimensional space frame problem. We will also discuss the computer program in parallel and then get the outputs by running this program, then finally assigning the values at the end reactions and checking for its accuracy from the analysis. So, let us now watch how we do a 3D analysis by taking a simple example. So, let us have a structural system as shown in the figure now. Okay. This is my structural system. Let us mark the dimensions of this. This is 3 meters. Okay. Let us say this is also 3 meters, and this height is also 3 meters. Let us mark the nodes as A, B, C and D. Let us say it is subjected to some uniform distributed load as shown on the screen now. The load intensity is 20 kilonewton per meter. The problem has certain constants, let us write down them. EIZ value is as same as EIY value, which is simply EI. GIX, that is the torsional constant, is taken as 1/4 of EI, and the axial rigidity constant is taken as again 1/4 of EI. The first job is to mark the local axis and global axis of the system and the coordinates. Let us mark the local axis and the global axis. Let us say the global axis is marked now, which is x, this as y and this as z. Let us now mark the local axis of each. Say this is my x m, y m, this 90 degree anticlockwise. So, y m and z m for the member A B. For the member B C, let us mark this as x m, 90 degree anticlockwise y m and 90 degree clockwise z m. For the member D C, let us say this is x m, 90 degree anticlockwise y m and 90 degree clockwise z. Okay. Let us mark the values in simple terms for this from the table. Let us say joint. Let us mark the x, y, z coordinates of all the joints. There are 4 joints 1, 2, 3, 4. Let us say A, B, C and D. If you look at the A joint, it is exactly at the origin of the reference axis. So, x, y, z is 0. If you look at the B joint, we have travelled 3 meters along x. So, plus 3 meters and y and z are exactly same. If you look at the joint C, we travelled 3 meters along x. and no travel along y, but minus 3 along z. If you look at the joint D, we have travelled 3 meters along x, and along y we travelled minus 3 and minus 3 along z. So, this coordinate system, which is going to be an input matrix for the analysis, can be established easily, no difficulty on that. Having said this, let us now mark the members and make a table for the transformation input. Let us say member, the length of the member, the joint designation of j and k, and then the direction cosines, which are Cx, Cy, Cz. Then let us also decide the type of transformation. Then let us find the psi angle by simple inspection. The members are AB, BC, and I should say DC or CD. The length of all the 3 members in meters are 3, 3.0, 3.0 and 3.0. For the member AB, the J and K joints are A and B respectively. This is B and C, and as far as this is concerned, this is D and C, because the origin of the DC member is at D. Now, let us talk about direction cosine. What is direction cosine? We already said that it is actually the angle between xm with x. Okay, let us look at this member with x, xm with y and xm with z. Okay, xm with x is 0. So, cos 0 is going to be 1.0 plus. As far as Cy and Cd is concerned, the angles are 90, therefore, they are going to be 0. Let us look at the member BC. Xm angle with x is 90. So, the cos 90 is going to be 0. Xm with y is again 90. So, that is again going to be 0. Xm and z are opposite. So, minus 1. Okay. So, 0, 0 and minus 1. Let us talk about the member CD, or let us say rather DC. Xm with x, global x 90 degrees, xm with global y exactly same. So, it is going to be 0 degree, and xm with global z 90 degrees. Therefore, I should say here 0 plus 1 and 0. So, there is no difficulty in establishing the direction cosine matrix for all the members. Okay, this can be obtained. Okay. Now, let us look at the member AB. X is oriented along x, so no problem. We should say I am going to practice YZX transformation. So, we are going to get psi y angle. Okay. And for the member BC, xm is oriented along z, therefore, I should do YZX transformation, and again I will get psi y angle. As far as the member DC is concerned, xm is oriented with y, I cannot do YZX. So, I should do ZYX transformation, I will get psi z by inspection. Let us try to find out what is the angle of psi. The angle of now psi y will be angle between ym and y. Let us say ym and y. So, it is 0. So, psi y is going to be, how do you check? Okay. So, psi y is going to be 0 degrees. Similarly, the angle between ym and y of the member BC, ym is here and y is here, again the angle is going to be 0. Let us mark 0 degrees. For the member DC, I am looking for angle between ym and y. Ym is horizontal, whereas y is vertical. So, the angle is going to be 90 degrees. So, I can easily estimate the psi y values for an input like this as a vector in my computer program. Okay. I can also input the type of transformation, because the psi angle actually depends on what transformation you are working at, correct. Now, let us mark the unrestrained and restrained degrees of freedom for this given problem. So, what I do is I draw the frame, let us mark the degrees of freedom unrestrained. So, along x, along y and along z. Let us mark the reference axis system. This is actually my y axis, this is actually my x axis, and this is my z axis, correct. So, let us mark displacements along x, y, z first. Okay. So, I should say this as delta bar 1, okay. Then delta bar 2, then delta bar 3, then I should also mark rotations about this, theta bar 4, theta bar 5 and theta bar 6 at the j at the end. Then let us mark here this joint is also unrestrained along x, seven, along y 8 and along z 9, then rotation 10, then rotation 11, then rotation 12. So, there are unrestrained degrees of freedom of 12 in number. Let us talk about the restrained degrees, which is again along x 13, 14, 15, 16, 17, 18, then here 19, 20, 21, 22, 23 and 24. So, total degrees of freedom are 24, out of which 12 are unrestrained degrees and remaining 12 are restrained degrees. I do not think there is any confusion in marking this, which is exactly same as that of the 2D analysis. Now, let us try to see how we can work out the direction cosine matrix and then how to get the transformation matrix. So, let us do that here itself. If I want to really do the C matrix, the C matrix actually is C 1 1, C 1 2, C 1 3, 2 1, 2 2, 2 3, similarly 3 1, 3 2, 3 3. What does it mean? C I j is actually the direction cosine of the angle between x m and the reference axis. So, what is the angle? This is the member 1, this is the member 2, this is the member 3. So, let us do it for C 1, okay, only for translation let us say. So, the angle between x m, let us also mark the local degrees x m, y m and z m for all the 3 members. Okay. Mark x m, y and z m, I am marking it here, x m, y m, okay, and let us say z m. I do not have space there, mark it here. For this member x m, Ym and Zm, origin here. For this member Xm anti-clockwise. So, Ym and Zm, okay, for this member. Now, let us write down the C1 matrix for this. The angle between Xm of the member and X of the member 0. So, cos 0 is going to be 1. The angle between Xm of the member and Y, which is 90 degree, cos 90 is 0. Angle between Xm of the member and Z, which is 90 again 0. Similarly, angle between Ym and X is 90, Ym and Y 0, that is cos 0 is 1, Ym and Z 90 becomes 0. Similarly, Zm and X 90 0, Zm and Y 90 0, Zm and Z 1. So, that becomes my C1 for translation. So, this is true at the jth and kth end. For rotation also it is true. Okay. Similarly, let us do it for C2. Angle between Xm and X is 90, okay, cos 90 is 0, Xm and Y is again 90. So, cos 90 is 0, Xm and Z is minus 1. Similarly, Ym and X 90 0, Ym and Y is 0 1, Ym and Z 90 0, Zm and X is 1, Zm and Y is 0, Zm and Z is again 0. So, that becomes my C2. Let us do for C3 matrix. Xm of C3 with X 90. So, 0, Xm with Y 1, Xm with Z 0, Ym with X 90, Ym with Y 90, Ym with Z 1, Zm with X 1, Zm with Y 90, Zm with Z 90. So, now I have the direction cosine matrices for all the 3 members, namely 1 2 3. So, we all know that the transformation matrix T is simply given by Cs of the member I, okay, then 0 0 and 0, similarly 0 Cs 0 0 0 0, which we derived already, is it not, and 0 0 0 0 and Cs, which is 12 by 12. So, one can easily find out this matrix. Let us then write down the global labels, okay, for each member. So, let us write down the global labels for each member. I can do it here. The global labels for the member 1, I will write down here. For the member AB, the global labels, okay. Looking at the jth and kth end, I should start with xyz translation at the jth end, rotation at xyz at the jth end, then translation xyz at kth end and rotation at xyz kth end. So, let us talk about that. So, easily you know translation x 13, then translation y 14, translation z 15 at the jth end, rotation about x 16, rotation about y 17, rotation about z 18, that is along the jth end. Then continuously I am writing it here. If you look at this space, it is going to be 1, is it not, 2, 3, 4, 5 and 6. So, that is going to be the label for member AB. Similarly, one can do for member BC and CD simply. For example, I fill up for BC for your convenience, starting from jth end, one can see here along x. So, I should say 1, 2, 3, 4, 5, 6, then kth end along x. So, 7, 8, 9, 10, 11, 12. Similarly, for CD, if you can write down, jth end is here, therefore, it is going to be simply 19, 20, 21, 22, 23 and 24. Similarly, for the kth end is going to be 7, 8, 9, 10, 11, 12. These are the labels. So, there is no problem in identifying the labels for these degrees of freedom. Let us now look at the computer program to solve this.